This video is going to cover the very beginning page and just a little bit of page 2, just in case you missed this first day of Unit 3 notes that we took together in class. So we're going to start by talking about the history of the periodic table, because this entire unit is focused on how the periodic table is organized, and even though it's organized a certain way now, it didn't start off that way. So the very first periodic table was created in 1790, and it wasn't even really technically a periodic table. It was mostly just a list of elements. We only had 23 elements discovered and known and established at that point in time, so it was pretty easy to just keep them organized in a list. But less than 100 years later, we knew of over 70 elements, and so that was a little bit more important that we start finding a way to organize these, because even just a list of 70 names, unless they're alphabetized or grouped a certain way, then it's going to take a long time to find a name in there. So this is when we started trying to organize all of these elements by something that would help us understand them and kind of find information about them more easily, hence the periodic table. And John Newlands was the first person to arrange elements according to their properties. The main property that he used was the atomic mass, because at this point we had the technology in order to measure precise numbers of atoms in a sample and, of course, mass very precisely with a lot of significant figures. And so we could do the math to figure out the average mass of an atom of a specific element. And so he arranged them from lightest to heaviest, and when he did that, he noticed some similar properties starting to occur. That like every 10th element in the list had this property, or every 15th or 16th element had this other property. And it started to be a little bit of a pattern emerging, and so he called these some periodic properties, and that's where the name periodic table comes from, is from this table organized using the atomic mass primarily, and then these periodic properties that started popping up. Now, even though Newlands was technically the first person to make any kind of periodic table, this next guy, Dmitri Mendeleev, is oftentimes referred to as the father of the periodic table, because he gets a lot of credit for how he improved upon Newland's table. So there's a lot of information here, and this one more than the last one, I might recommend you don't necessarily need to write the green stuff. The purple stuff here is the most important stuff that you know about each of these people, and the green stuff kind of just helps introduce or kind of refine that information to give you some more context for it. So Mendeleev took Newland's rows and his kind of periodic table and started looking deeper into all of these properties and these patterns that were emerging when he was organizing them by that atomic mass. And he actually took those rows and turned them into Mendeleev's columns, and he used the way that our elements react with oxygen to do that. And I'm going to kind of go a little bit off of these notes for a second to explain that, because this is really important that you understand kind of why Mendeleev got so much credit when Newlands didn't. So Mendeleev was studying how elements react with oxygen, and let's just leave X as any element. Well, he was studying how it forms a compound with O, and what he noticed was that in this list of elements, there would be something that bonded in a ratio of 2-to-1 with oxygen, and then one that was bonding 1-to-1 with oxygen, and then one that went 2-to-3 with oxygen, and then XO2 with oxygen, and so on. And there were more different formulas, but basically what he saw was the first 4 elements on the list essentially bonded with oxygen in a certain way, and then the next 4 elements on the list, even though they are bigger masses, and that's how he was still looking at these as organized by mass, these were all heavier than those first 4, but we still saw this same pattern of X2O, XO, X2O3, XO2. And so when he arranged them in smallest to largest atomic mass order, started seeing this regularly predictable pattern in how these elements bonded with oxygen. And so he cut the list at the end of each repeat of the pattern, and then he made the line a list of elements just continue on that next row, and then kept ending that there, and then maybe the next element in the row, sure, is X2O. That one's even heavier, and that one would be the first one on the next row. So they looked at these properties, and the way they reacted with oxygen just left no doubt in their mind that this had to be some predictable pattern. And this last bit of the Mendeleev definition is actually really important as well, and kind of just mind-blowing for the time. Well, he noticed that his pattern seemed perfect for rows and rows and rows, and then all of a sudden, his pattern would go from an element that bonds 1-to-1 with oxygen to an element that bonds in a 1-to-2 ratio with oxygen. And there was no element that bonded in a 2-to-3 ratio with oxygen. And instead of throwing up his hands and saying, well, I guess my pattern is broken, it doesn't match, like, this is impossible, like, it doesn't fit all of the situations, I must be wrong, he said, well, maybe we just haven't discovered an element yet. Maybe there will be an element that will bond in this ratio to oxygen and have a mass in between the elements that have these other formulas with oxygen on either side. And he went on and he predicted not only that there would be elements in some of these spaces, but its density, its reactivity, all of these different properties, because he was able to compare it to the elements around that empty space in his periodic table. And he had this whole list of properties for an element that had never been discovered yet. And what's so mind-blowing about it is even within his own lifetime, people discovered those elements. I believe gallium was one of them. And so they discovered this element. They managed to get it out of this ore in this obscure mountain range. And they made this paper and sent it out worldwide. We've discovered this. We've named it gallium. It has all of these properties. And Mendeleev was like, yeah, no, I knew that was there. Like, I knew it was somewhere. So good job. Yeah, your numbers agree with mine. And he had studied this element without ever having seen it or had his hands on it. And even in some cases, I believe, he was like, maybe you should check your numbers, because I think I predicted its density would be more like this. And they're like, oh, yeah, maybe that wasn't pure. Maybe we should check our numbers. Mendeleev's periodic table was so powerful at the time and so groundbreaking for exactly what he did with it and the way that he accepted these blank holes. So, all of that aside, Mendeleev is considered the father of the periodic table with very many good reasons. Intriguing study. If you're interested, look it up. There's so much more to his life and his discoveries than just this. Just 1-2 lines. Then along the way, we had Moseley come along, and he was the first one to actually arrange the elements by atomic number, which for the most part corresponded to the atomic mass, but there are a couple of key differences there. And he didn't actually know that the atomic number he was using was the number of protons in the nucleus, but he was able to find this unique number for each element, the charge of the nucleus, and use it to organize his periodic table. So just know he was the first one to use the atomic number to organize it like what we use today. And all of these scientists were kind of establishing what we now call the periodic law, which the long, wordy definition is that when elements are arranged in increasing atomic number, there's a repeating pattern of physical and chemical properties. The short version of that, though, is that an element's properties depend on their atomic number, which is something we've been talking about since the beginning of Unit 2, when we established that every element has its own unique atomic number, which is the number of protons. That's what makes the element what it is. So it's an important idea for the atom itself, and it's an important idea for how the periodic table helps us understand the atom and its structure. So those are the three guys that you really need to know, and the kind of the basics surrounding the establishment of the periodic table. Now let's actually look at this little mini periodic table that you've got down right below that history stuff, and let's start learning a little bit more about how it's organized. The first thing, and I think the most important anytime you look at a periodic table, is going to be to find this stair-step line. And yours isn't drawn in yet, so I want you to go ahead and draw this in. The important thing is that you start by drawing a line right underneath the boron. And once you get that started, you go over one under boron, and then down by aluminum. And you just keep going over and down until you have a nice, bold, hopefully not covering up too much of those elements' symbols there. But this bold stair-step line here is the dividing line between our metals and our non-metals. And so it might be a good idea for you to color code your periodic table, or at least write non-metals and maybe draw an arrow to them. And the important thing about this arrow is there's actually one non-metal that is hiding over here. I'm going to color code each element's square. So most of our nonmetals are here to the right of the staircase, but hydrogen is over there with the metals because it has one valence electron, and that's kind of where it fits in terms of reactivity a little bit better. And other than these nonmetals that I've just highlighted red, everything else on this periodic table is a metal. Even those F block elements down below are inner transition metals. So everything else is a metal. And we do have some special groups of these metals and nonmetals that we're going to talk about, but it's important that you can always look at the periodic table. It's going to become more and more important in this class that you can find these metals and these nonmetals. So the next thing that I actually want you to write in here, and I'm going to have this pop back up in a second, is that we're going to talk about some special groups, but it's probably a little important for you in general to know that when we talk about groups, we mean the columns of the periodic table. So go ahead and write that there. Remind your future self, because eventually you will forget or get confused by that. And then might as well add in there another vocab word. The periods of the periodic table are our rows. So groups are columns, sometimes also called families, and periods are rows. We're going to talk about some special groups, like I said, but I want to talk about one more than what we've actually seen so far, those transition metals. So these are the ones we're going to find on the periodic table and compare the reactivity of. And so back to the top, our alkali metals are in group 1. That is this first column of the periodic table here, lithium to francium. Hydrogen is not an alkali metal because it is not a metal. And remember that these elements in this first column all have one valence electron. And while it might seem like they're a little bit far away from that full octet that they want, that full 8 valence electrons, remember all they have to actually do is lose that one valence electron, and then the layer, the energy level under the valence electrons, becomes the valence electrons, and it's already full. So they are just one electron away from that octet rule and being stable and happy. So they're actually pretty aggressive about going and getting rid of that electron, which means that they have the highest reactivity of all of the metals. The alkaline earth metals are right next to them in the second column. I remember the difference. These names are so similar, and they're so close together on the periodic table as well. I remember the difference between them because that second column of metals has 2 names, and the first column of metals has 1 name. So these alkaline earth metals are also fairly close to being happy and full with their 8 valence electrons, but they do have to lose 2 electrons compared to that first column's 1. So they are high reactivity, but not quite as reactive as that first group. Now, I actually want to real quick jump down to our transition metals. These are all the rest of the metals after our alkaline earth metals. It actually goes all the way over to that staircase. So all of these elements in the D block all the way to that staircase are what are called transition metals. So if it's not an alkali metal or an alkaline earth metals, then it is a transition metal. And then we have these F block elements actually that are called inner transition metals, but they're still kind of sort of transition metals when it comes down to it. But we're not going to do a whole lot with that F block in general, and not especially in this unit. And so these are mainly the elements in column 3 through 12, which is that D block. Then remember that this goes all the way over to that staircase technically. And these metals in general have lower reactivity than the rest. There is still kind of a wide variety, but there is a sharp decline in the reactivity of the metals when we go from the alkaline earth metals into the transition metals. And so they're all generally low, but some are lower than others. Now, I skipped down to those transition metals because that has now covered all of our metals. These last two special groups are both non-metals in general. So the first one that we're going to talk about is our halogens, and these halogens are group 17, and they have 7 valence electrons, which means that they're going to be pretty aggressive about going out and finding one more electron so they can get 8 and be happy and full and stable. So these are the highest reactivity of our non-metals, but I don't really like having two that say highest. If you write highest non-metal because you already wrote highest metal here, that will work for me. But in general, what I kind of think of these as, they are about as reactive as those alkali metals, but I'm just going to call this very high in general. And then our noble gases, which are actually that very last column, we've already talked about them a little bit. Those noble gases in group 18 have no reactivity. They do not react because they already have all 8 valence electrons that they want. Another word for that is inert. They do not react. Even if another element wants to, they don't want to, and so they will not react. So, at the bottom of the page, I want to try and get you to practice putting all of this together. So, I'm going to do this first row with you and then ask you to do the rest. And as you can see, in the rest of this table, there are some spaces where you won't be able to fill in an answer, so you can go ahead and cross these out. And so, here, in this first row, our configuration is He2S2 2P5. And if you look at a periodic table, then that is going to point us directly towards fluorine. And if you remember, that block over there is the P block, and that kind of makes sense because that's where our configuration ended here, was in the P block. And the period, the row of fluorine, is the second row. I know it's technically the top row of the P block, but it is the second row of the periodic table overall. Its group number is 17, and that whole group are called halogens, like we just learned and talked about earlier. And this is a non-metal. These are the only two types of elements that we're worried about here, metal or non-metal. And it is the highest reactivity of all of the non-metals. I think that my final answer on my notes above was just very high, but either one works for us here. So I want you to fill in the rest of this table by yourself. You will need a periodic table. I'll go ahead and pull one up on the screen here for a moment so you can pause it, use that to fill that in, and check with me if you're unsure of any of these answers. So here is that. And now, over here on the next page, we're just going to finish out these two definitions and then you're done. So, these two definitions are really important, and I am going to kind of talk about them each time we learn a new trend, but these are the reason why everything this unit happens the way it does. So these are two important words that it's really important to understand before we start talking about all the rest of the stuff that we're going to learn this unit. So, we're actually going to start with the nuclear charge. And just like it sounds like, nuclear charge is the charge of the nucleus. And the only thing that has a charge in that nucleus are the protons. So this nuclear charge is equal to the number of protons. And while it might seem like this will change and every single element will have a different nuclear charge, this actually only is going to increase going from the left to the right in the rows of the periodic table. And I have an example on the next slide that I'm going to show you that helps you understand why this doesn't change vertically within a column, only across rows as we move left to right. And it's kind of because it's not the total nuclear charge that we care about, the total number of protons, but the effective nuclear charge, the charge that the outermost electrons can actually feel in the atom. But we'll talk about that in a moment. The other word that we need to know and understand is shielding effect. And this is a little bit more complicated, but not too bad. Shielding effect is the effect caused by the inner energy levels of electrons canceling out part of the nuclear charge for the outer electrons. So what that means, and what we're going to kind of see and talk about on the next slide, is that nucleus with its positive charge is pulling on all of the electrons and all of those energy levels around it. But the electrons on the outermost energy level, and the farther out they are, and the more energy levels underneath them that they are, the more of that nuclear pull gets canceled out on the way to those outer electrons. So that first energy level has no protection, no energy level between it and the nucleus. So it feels the full pull, the full force of the pull of all of the protons in the nucleus. But the outer electrons only feel a little bit of that pull because those protons are being kind of used up. Essentially, they're not really being used up. The charge is being used up and kind of used to pull on those inner electrons, and it's not really getting all the way out to those outer electrons. So that's our shielding effect. And these two words really important for our trends. And this shielding effect is going to increase as we go down the columns of the periodic table. Because as we go down the periodic table, we go from the 1s to the 2s to the 3s to the 4s. Each of those is adding another energy level around our atom. So having these ideas in our head is going to really help you understand these trends that we're talking about and why they happen the way they do. So let me use a little quick visual here to help you understand these two words and how they relate to each other. I have some simple examples of hydrogen and lithium drawn out here. As you can see, our hydrogen is element number 1 on the periodic table. It has 1 proton in that nucleus, which means that its total nuclear charge is a positive 1. Our lithium atom has 3 protons in its nucleus and 3 electrons around the outside as well. But that means that we have a positive 3 as our nuclear charge. It's the total nuclear charge, though. What we were talking about a moment ago, and what I mentioned on the previous slide, is that it's not the total nuclear charge that really matters. It's the effective nuclear charge. And so here in hydrogen, that 1 electron and that 1 energy level feels the full pull of that nucleus, that 1 proton on it. So it feels a +1 effective nuclear charge, same as it always does. And then over here in our lithium atom, this outermost electron is only going to feel 1 of those protons pulling on it. The other 2 are getting canceled out by these 2 inner electrons. So even though the full 3 are trying to pull on that electron, this kind of shell, this area, this first energy level with those 2 electrons, it's like a -2 shell that cancels out some of the pull, so that this lithium electron, that outermost valence electron on lithium, still only feels the pull of 1 single electron on it. So the fact that that inner energy level is protecting the outer energy level is the shielding effect. And what this is also showing you is that because hydrogen and lithium are in the same column, they still both have that 1 valence electron. And what you're seeing here is that they both feel the same effective nuclear charge on that outermost electron. So that's why that nuclear charge doesn't actually increase as we go down a column in the periodic table. Even though there's more and more protons in that nucleus, there's also more and more shielding happening. So that outermost electron is getting held weaker and weaker compared to the ones above it. It's just got the same amount of pull on it overall. So that's really it for now. We'll talk about these ideas over and over again with each of the trends, but I wanted to get you the basic idea of what they were here.